All right, greetings YouTube, Beautiful Mind here. This presentation will serve as the lecture for week 6 Friday for Calculus 1. A few announcements or slash notes for the students. One, be sure that you've completed the participation and honesty quiz via Moodle. 2, there is an assessment on Moodle that's available. That's also going to serve as a quiz grade. So you get 1 attempt. It's timed. So just whenever you have time to kind of sit and focus on it, you want to do that. So there are 2 quizzes on Moodle. You want to definitely make sure that you're getting credit for those. Let's see. So I was kind of trying to get a sense of where I want to go. I know I don't want to go beyond chapter 5, and I would like to talk about chapter 5. In chapter 4, I might go up to maybe 4.7 possibly, but I definitely want to touch on chapter 5, integration. Integration is the other part of calculus, like the other half of calculus that we really need. And obviously we're kind of entering the home stretch. I don't really want to go beyond chapter 5, and I know that'll get us to pretty much to the end of the quarter, and it'll have us talk about what we need to talk about. My intent is to load as many assignments for the remainder of the quarter as possible and relax the late penalty from 20% to 10%. So what that means is that you can honestly work on any old assignments and increase the score to an A, you know, for either late or missed assignments, right? So it's you can honestly get pretty much whatever score you want. It's just a matter of making a decision, making a plan, and executing the plan, okay? You have support for this material. I'm available for dedicated YouTube videos, live Zoom sessions. We also have the tutors. The tutors can definitely help with this. And you also have each other, and you have Pearson, and you have the internet, right? So between any combination of those sources, you should be able to kind of digest this information, okay? And it's very possible for any student in the course to get essentially whatever grade they want, whatever letter grade, right? It's very possible. Okay, also on that note, we're going to take some time. So we want to continue the discussion of derivatives in chapter 4, and we want to look at optimization problems. So last time we looked at how to find the critical values and how to graph functions, right? And so that allows us to find key important features of graphs or of functions and actually hone in on those exact locations. For instance, like in college algebra, if we were trying to graph a polynomial, we could get a sense of like if it's a W or if it's an S or what the general shape, but in college algebra we couldn't find the exact local or relative maxima and minima. But now with calculus and setting the derivative to 0 and this discussion on the first derivative and second derivative, we can actually locate those features of graphs whenever the function is continuous and differentiable on the open. Is continuous on the closed interval and differentiable on the open interval, right? With some conditions, we can actually locate those key features of graphs, right? So with the ability to locate like the relative max and the min and these other features of the graphs, we can talk about optimization, right? So we'll have like a real world scenario where we can model it with we can, model the data. We can fit the data to some model, and then based on the model, we can find a relative max, relative min, and we can optimize, either maximize or minimize the function, right? Typically, like if it's a cost function, we want to minimize the cost. If it's like a profit function, we want to maximize profit. If it's like a distance function, we typically want to minimize distance, right? It depends on the context, but that's the general gist of it, right? So that's what this section is about. The theme of this section is optimization, a topic arising in many disciplines that rely on mathematics. A structural engineer may seek the dimensions of a beam that maximizes strength for a specific cost, a specified cost. A packaging designer may seek the dimensions of a container that maximize the volume of the container for a given surface area. Airline strategists need to find the best allocation of airlines amongst several hubs to minimize fuel costs and maximize passenger miles. In all of these examples, the challenge is to find an efficient way of consuming or efficient way to carry out a task where efficient could mean least expensive, most profitable, least time carry out, least time consuming, or as you will see in any other measures. To introduce the ideas behind optimizations, think about pairs of non-negative real numbers x and y between 0 and 20. with the property that they add up to 20. That is, x plus y equals 20. Of all the possible pairs, which has the greatest product? So table 4.3 displays a few cases showing how the products of two non-negative numbers varies while their sum remains constant. So the condition that x plus y equals 20 is called a constraint. It tells us to consider only non-negative values of x and y satisfying this equation. The quantity we wish to maximize or minimize in other cases is called the objective function. In this case, the objective function of the product P is going to be x times y. From table 4.3, it appears that the product is greatest if both x and y are near the middle of the interval 0 to 20. This simple problem has all the essential features of optimization problems. At their heart, optimization problems take the following form. What is the maximum or minimum value of an objective function subject to some given constraints? Okay. So you see here we have like x plus y equals 20. So therefore y is going to be 20 minus x. And then substituting that into the product function, we get 20x minus x squared, so which is a function of a single variable. So then notice that the values of x lie in the interval 0 to 20, where p equals 0 and p is 0 and p of 20 both equal 0. So then we maximize, right? We notice that the highest exponent is a 2, so it's a parabola. The leading coefficient is negative, so it's going to be a downward facing parabola. If we have a downward facing parabola where the vertex is between 0 and 20, and we want to optimize this, you know, the maximum is going to occur at the vertex, right? So we could find that using calculus. Okay, so I think the gist is there. I want to kind of look at an example. Okay, so let's look at this example. So we have the rancher's dilemma. A rancher has 400 feet of fence for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions as shown in figure 4.58. What are the dimensions of the corral that maximize the enclosed area? What is the area of that corral? Okay, so let's look at the image that corresponds to it. Figure 4.58. We actually need to kind of go forward a little bit. Here it is. So this is the image that we're working with. All right, so we see the barn. We see the fence. Let me get a copy of this. We don't need that one. Delete. And this one. This. Okay, and let's put that closer to where we're working, which is here. Cool. All right. So again, so the blue represents the fencing, and we have the constraint. So let me see. So we have 4 times x plus y. The total fencing is going to be $400, and we want to maximize the area. Now the area of this region is going to be what? Basically x times y. That looks right. So again, a rancher has 400 feet of fencing for constructing a rectangular corral. One side of the corral will be formed by a barn and requires no fence. 3 exterior fences and 2 interior fences partition the corral into 3 rectangular regions as shown. What are the dimensions of the corral to maximize the enclosed area? Okay, so I'm just going to work this from the way I see it. Okay. And yeah, that should be fine. Okay, so we have this image. So we have that 4x plus y equals 400, right? We want to maximize the area. So let's maximize the area, which is going to be, it should just be x times y, right? The area of this region. So from the constraint, if we have that 4x plus y equals 400, let's solve for y. So then y is going to be 400 minus 4x, right? Then let's take this and put it into our area function. So now at this point, we can express the area only in terms of x. and that's going to be x times y, but y is 400 minus 4x, right? So now we have the area in terms of one variable, right? So if we want to maximize this, all right, so let's look at the derivatives. Let's look at a prime of x. That's going to give us, I'm going to go ahead and distribute. We're going to have we're going to want the derivative with respect to x of 400x minus 4x squared, right? Let's add a page. Okay. So notice that with the area function, the highest exponent is degree 2, right? So if we were to graph the area function, it would be a downward facing parabola. So then we would anticipate the area to be maximized at the vertex, right? So we could find that vertex by observing the first derivative. Let's see. So let's take the derivative of this, and we're going to have the derivative of 400x is just going to be 400 minus 8x, right? So then to identify the critical value, we want to set the derivative to 0 and solve. If we add 8x, we're going to get 8x equals 400. So then we get x equals, what is that, 50. And then just to make sure that we can verify that it's concave down, let's go ahead and just look at the second derivative, right? So the second derivative is going to be d by dx of 400 minus 8x, which is just going to be negative 8, which means that it's concave down, okay? Which means that we would have a maximum value, right, at this critical value. Okay. So then when x is 50, we could find, so we can actually solve for y. So we said that y is going to be equal to 400 minus 4x. So 400 minus 4x, which is going to be 400 minus 4 times 50. And that's going to be 4 times 5 is 20, so that's 200. So 400 minus 200, which is 200. Okay. Now let's get some units here. It should be feet. Feet, right? So we have x is 50 feet. Y is 200 feet, okay? And the area when x is 50 feet is going to be 50 times 400 minus 4 times 50, okay? That's going to be 50 times 200, 200. So 10 with 3 zeros. Feet squared, right? So our claim is that this is the area, this is our y value, and this is our x value, okay? Now we could confirm in the context of the original, just for the sake of time. I'm just going to kind of glance at the answer, okay? Let's see, how do we do? So we said x was 50, y was 200. Let's see, how do we do? Okay, so the solution that they have, hit something. Let's just go here. So the solution that they have, they first sketched the graph. We have that. So then we had y equals to 400 minus 4x. So then they get the area only in terms of x. They looked at the first derivative. So if we graph the area in terms of x, we get this. So the optimum is going to occur at the vertex. And so when x is 50, the optimum area is 10,000 feet squared. I think we got all of that, right? So it says, therefore, the maximum area of 10,000 feet squared is achieved when x is 50 feet and y is 200 feet. The objective function A is shown. Okay. All right, let's try another one. Let's do another one. So we have this example too. Let's, I think that's the right one. Let's add a page. Okay, we have this example too. So airline regulations. Suppose an airline policy states that all baggage must be box shaped with a sum of a sum of length, width, and height not exceeding 64 inches, okay? What are the dimensions and the volume of a square-based box with the greatest volume under these conditions? Okay. Greatest volume. So that means we want to maximize the volume. And we have the constraints, right? So let's go like this, right? You see the box there. I guess we could start by drawing an image, right? Let's do like this, paper. Let's get some graph paper. So we're working example 2 where we want to maximize the volume. So we have a box. I guess I could just take that one. Let's just copy it from here. Okay. All right. So we have this box. All right. So I was trying to ignore this, but I'll just put it over to the side. So if we have the box, now we're given the constraints that the length plus the width plus the height is less than or equal to. Okay, so it should be less than or equal to, but I'm just gonna, they have it set to equal to 64, so it can be up to, at most it could be up to 64 inches, right? Since it's a square base, the length and the width are both W, so W plus W is going to be 2W plus the height is going to be 64 inches. The volume, we want to maximize the volume, right? And the volume is going to be basically what? Length times the width times the height. But since it has a square base, the length and the width, this is going to be W squared times the height. So we can actually solve for the height from the constraint. So the height is going to be 64 minus 2W. All right. So then here we can plug in that H and we're going to get W squared times 64 minus 2W. All right. So we want to maximize the volume. So now we have the volume expressed in terms of the width alone. All right. Is going to be W squared times 64 minus 2W. So notice that the highest exponent is going to be power of 3. The leading coefficient is going to be negative. So that means that the graph of this volume is going to go down to the right. It's a polynomial. The long-term behavior is going to go down to the right, up to the left. So we can anticipate a relative max and a min somewhere, on the graph, right? So if this is our volume, let's go ahead and rewrite this volume. So the volume, if we distribute like this. Okay. We're going to have 64W squared minus 2W cubed. Okay. So then let's go ahead and observe the derivative and the second derivative of the volume. So we're going to look at V prime of W. What is that? 128W minus 6W squared. And then let's go ahead and look at V double prime of W, which is going to be 128 minus 12W. Okay. So if we want to find the critical values of W, we need to set the derivative to 0. All right. Let's add a page. Let's set the derivative to 0 and see what happens. So if we say V prime of W, which is going to be the 128W minus 6W squared, we want to set that to 0 to identify our critical values. Okay, we could factor out what is 6W. Let's factor out 6W. What is that? 2? No, not 6. We can't do 6. Oops. Okay. Let's try, let me see, 3 and 8 is 11. Let's do 2W. So that becomes a 64. 6 and 4 is 10, right? Minus 3W equals 0. 128 and 6, okay? So then from here, we get 2W equals 0, or 64 minus 3W equals 0. So then W equals 0, or if we add and divide, W equals 2, 1 point and a third, right? So 0.3 bar. So then we would have critical values when W is 0 or when W is 21.3. I think that's correct. 63, 64, okay. So then let's look at the second derivative and let's evaluate these values of W on the second derivative. And if it's positive, that means it's concave up. If it's negative, it's going to be concave down. So we have that the second derivative is going to be 128 minus 12W. So let's first evaluate when W is equal to 0, right? So V double prime of 0 is going to be what? 128 minus 2 times 0, which is just 128, which is positive. So that means it's concave up when W is 0. Let's evaluate when W is equal to this 21.3 bar. All right. So then we have V double prime of 21.3 bar. That's going to be 128 minus 2 times that 21.3 bar. Okay. That's going to be what, like 42 times that is 42, 43. It's going to be positive. Is that right? Shouldn't it be negative? Concave up. Is there another? How could this happen? I'm trying to get an image in my mind. Oh, it's positive. 28. Let me see. If I add and divide, I get that the second derivative is positive here as well. So maybe it kind of like flattens out. Let me look at the original. Cubed. Instead of going up and hump, it could go. I feel like we made a mistake somewhere. Let me see. Let me back up. 128 W minus 6W squared V prime. We could factor out a 2W. 64 minus 3W. So that's 0. 21 and a third. I guess I was anticipating one of them to be concave up and one to be concave down. Let me see. So I feel like I made a mistake somewhere. Let me see. Oh, I see my mistake. Okay, I found it. I was like, yeah, something's not right. Okay. It's not 2. This is supposed to be 12. And this is supposed to be 12. Yeah, that's what happens when you write in a small, when you try to jam it in and you're moving fast. Okay, I was like, yeah, something's not right. Again, I was anticipating one of them to be concave down, so then we would have a maximum value. Okay, we found it. Ooh, I was like, what is going on there? Okay, so here, right, we have V double prime of 21.3 bar, 128 minus 12 times this 21.3 bar. Okay, so now, I think I'm gonna just use my calculator. Let me see. I know that's 213. It's essentially going to be negative, which is what we wanted. If we say the 128 minus that part on the right, the second derivative is going to be negative at that point, which is what we were anticipating. So now that we have our negative second derivative at that critical value, that means it's concave down, which means we should have a relative max at that value of W, right? Okay. So then with W is 21.3, okay? Let's see. Let's go back to the question. What are the dimensions and volume of a square base box with the greatest volume under these conditions? So now our claim is that the volume is maximized when the width is 21.3. What are the units? Give me a moment. And we're back. I had to sneeze. I just didn't want to sneeze into the microphone. Inches, right? So our claim is that the volume is maximized when we have 21.3 inches, when that's the width. So then we had an expression for the height, 64 minus 2W. So earlier we said that the height was 64 minus 2W. So then that's going to be 64 minus 2 times 21.3. What's that, 43? No. 42 plus 2/3. So then that's going to be 64 minus 42.6 bar. So if that was 43, that's a 3. If that was 50, it would be 14 plus 7 is 21 1/3, right? "21 inches, shy of 2 feet." That's about right. Okay. Sounds like a box. Like the width, length, width, and height, they're all 21.3 inches cubed, or inches. It looks like it's 21.3 bar by 21.3 bar by 21.3, and these are all inches. And then the volume is going to be that cubed. Okay. Okay. Let's see, how do we do? That's what I got when I did it. Let's see how do we do. Okay. 64W squared. I think we got that. The volume of the function is going to be 64 divided by 3. V of 64 divided by 3. The 9709 cubic inches. Let me see if I get that number. 21. We got what? 21.3. Let's do this. Hey Google, what's 21.3 to the power of 3?
The answer is 9,663.597.
63, 9,000. So I feel like we're off. Let's see. 64 divided by 3. That's a 2. Yeah. Hey Siri. Never mind. I didn't mean to say Siri. Never mind. Hey Google, what's 21? Oh, I see, because I did 0.3. Cancel.
Sorry, I don't know how to help with that yet.
Hey Google, what's 21 1/3 cubed?
The answer is approximately approximately 30,762.
Let me try it like this. Hey Google, what's 21 plus a third? I said that wrong. Cancel. Let me try this. Hey Google, what's 21.3 bar cubed?
21.3 cubed is 9,660.
No, that's not right. 0.3. Hey Google, what's parentheses 21 plus a third close parentheses to the power of 3?
The answer is approximately 9,709.037.
Whoop, 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 whoop. So we actually got it right. I was just inputting into the calculator wrong. Because when I said 0.3, that's different than 3 bar. So that's why we got the wrong volume initially. But we got the idea. All right, the gist is there. So the 21.3 is correct. And then the dimensions. Let me see if I can find the dimensions here. W is 64 inches. 64 minus 2W. So the optimal box is a cube, right? Yeah. Yeah, so the optimal box is a cube. We got that the length, the width, and the height were all 21 and a third. Okay. So this was good, all right? That actually worked. Let me see my time. We're good on time. So I'm gonna let those be. I know that was a little bit intense, but that's how it goes. And I definitely have made a mistake. And again, it was supposed to be 12, not 2. I had done 2 earlier. Okay. That was what, example 2. Let's just do another one. Let's give it another one a go. Right here. We have this example. So walking and swimming. Suppose we're standing on the shore of a circular pond with a radius of 1 mile, and we want to get to a point on the shore directly opposite our position on the other end of a diameter. We plan to swim at 2 miles per hour from our current position to another point on the shore and then walk at a 3 mile hour along the shore to the terminal point. How should you choose P to minimize the total time for the trip? Figure 4.62. Let's look at figure 4.62. Okay. So we have our starting position. We're going to swim and then walk. So how do we choose that point P to optimize? Okay, let's get a sense. Let's do this again. We're standing on the shore of a circle with a radius of 1 mile. We want to get to a point on the shore directly opposite at the other end. We plan to swim at 2 miles per hour. So it sounds like distance equals rate times time to another point P. Then walk at 3 miles per hour. Let me think about this one. So the chord length, we have arc length, which is fine. We could use a lot of cosines there, but let's see on that. Give me a moment. I gotta think about this one. Yeah, so we definitely said that arc length is S equals R theta, but let me see, for chord length, 2R sine of theta over 2. So from there to there, because it makes a right triangle, right? So, okay. So if we're looking at chord length, right? Let's look at this image here. Suppose we ignore the bottom triangle. Or, okay, so I'm trying to get a sense of this chord length, right? So say we focus on this triangle here, where this angle apparently is going to be theta over 2, right? So if we want this, and this is theta over 2, shouldn't that just be, that's the y value, which is our sine, right? So it looks like sine of theta over 2 is going to give us this over this. Think about it. So sine of this is going to give us this over this. So sine of theta over 2 is going to give us half the chord length divided by r, right? Let's write that out. So again, if we just focus on that upper triangle, right, we have the chord length. So from pre-cal, right, this represents half the chord length. This is theta over 2, and this is the radius of the circle. So then from pre-cal, this is a right triangle. So then sine of theta over 2 is going to be half the chord length. So I'm half the chord length divided by r, right? So that means half the chord length is going to be r times the sine of theta over 2. But if we don't want half the chord length, we want the whole, so we need to multiply both sides by 2. So then the chord length is going to be 2r times the sine of theta over 2. Okay, that was a bit of a stretch, but it makes sense. So now that we have the chord length is going to be 2r times the sine of theta over 2, that's fine. So now we have our chord length in terms of the radius and the central angle theta. And then also, so from pre-cal, we said that what the arc length is going to be r theta, or again, theta has to be in radians, okay? So then we can solve for one in terms of the other. Now we have the radius, so we have the chord length in terms of the central angle theta, and we have the arc length in terms of the central angle theta. So we can write one in terms of the other. Let me see, what do we want to... We want to minimize. How should you choose P to minimize the total time for the trip? Let me think about it. So we know that R is 1 mile, right? So both of those R's can essentially become 1. So we have each one in terms of theta. Let me think about it. Okay, let me think about it. So they are using distance equals rate times time. Let's see. All right, let me see if I can fit this to the charts like how we used to do in college algebra, right? So I'm kind of doing this on the fly, so you have to bear with me. So I'm going to use rate times time equals distance. Distance equals rate times time. Okay. We have two parts. We have the part where he's swimming, and then we have the part where he's walking. All right. So we want to look at the table created by these scenarios. Okay. We want to minimize the time. Let me see if I can get it to fit. Okay, we do have other information, right? It says the radius is 1 mile. We want to get to the pond. We swim at 2 miles per hour. So the rate swimming is, and the units here are miles per hour. So we swim at 2 miles per hour. That's going to take some unknown amount of time, t. So then that distance, it's going to be 2 times t. Let me think about it. Oh, again, we have an expression for the chord is going to be given by that. That's the distance, right? I'm going to let this be for right now. So then it says that when he walks at 3 miles per hour. Oof. So again, 3 miles per hour. I'm going to call this T1. That's going to take a different amount of time, so I'm going to call this T2. So 3 times T2. Okay. I feel like it's getting a little bit worse. Let me see. If it takes some... Okay. Let's see. So now we know the distance when he swims, right? The distance when he swims is going to be that 2r. So if we let r be 1 mile, 2 times the sine of theta over 2, right? So 2t1 should be 2 times the sine of theta over 2. That's what's the relation? Okay, yeah, we can get an expression for t1 from here, right? So ultimately we get that t1 equals the sine of theta over 2. Okay, we're gonna let that be. And then when he walks, so the 3 times t2, that's going to be the arc length, which is r times theta, and r is 1. So then 3 times t2 is just going to be theta in this context. So then t2 is going to be theta over 3, right? So now we have t1 in terms of theta, t2 in terms of theta. So then we want to minimize his total time. I'm going to just call his total time t, which is going to be basically t1 plus t2. All right, that was a little bit of a stretch, right? So what we could have done, instead of writing as t2, we could have said, oh, well, t2 is going to be the total time minus t1. But this is fine. I'm going to go with this, right? So now let's just plug in. So then the total time is going to be based on, let me think about this. Yeah, I think this is okay. Let's keep going and see where it goes. So t1, which is going to be the sine of theta over 2, plus t2, which is going to be theta over 3. Okay. And we want to minimize this. Okay. Okay, let's go with it. Let's go with it and just see what happens. A little bit of stretching, but we're going to see what happens. What's the time? Okay. So now we have the total time in terms of theta alone. So if we look at, so again, this was t of, here, let's move this down here. So then t of theta, the original was sine of theta over 2 plus theta over 3, okay? So then if we look at the derivative with respect to theta, the derivative of sine is cosine theta over 2 times the derivative of the inside function, which is just a half, plus a third. Okay, I think this is good. I know I'm missing like maybe like some of my domain discussion, but I'm just trying to see where this train of thought goes. And I'm tempted to go ahead and look at the second derivative as well, just to be consistent like how we did the other. So the second derivative based on theta. Derivative of cosine is negative sine theta over 2. The half just persists times another half. And then the second term goes to 0. All right, so then ultimately this is going to be negative 1 by 4 times the sine of theta over 2. Okay. All right. So then to find the critical values or points of consideration, we want to set the first derivative to 0. So if we look at t prime of theta, which we have as 1/2 cosine of theta over 2 plus a third, we want to set that equal to 0. Okay. If we set it to 0 and solve, let me see, subtract. So then we get cosine of theta over 2, negative 2 by 3. Okay. So let's see, cosine is some angle. I guess we could just use the inverse trig. Cosine of what angle gives us a negative 2 by 3? Or if we're going to use inverse trig, remember that the domain for cosine was restricted from 0 to 180 and the range were from negative 1 to 1. So then the domain for, okay, so then our claim is that so the domain for inverse cosine, it has to be from where? Negative 1 to 1, and the negative 2/3 is from negative 1 to 1, so we're in the clear there. So then theta over 2 is going to be inverse cosine of this negative 2 by 3. Let me think about it. And the output has to go from 0 to 180, right? Because that was the range, that was the domain of cosine, or the range of inverse cosine. So then ultimately theta, let's calculate that number. All right, a little bit of a stretch, but that's how it goes. Let's go here. What's the time? All right, and we should be doing all this in radians also, by the way, because that's what we need for arc length. First, I'm going to do it in degrees just to get a sense of where it is. So if we do inverse cosine, inverse cosine of a negative 2 by 3 in degrees, that's 131 degrees, 0 to 180. So that is within 0 to 180. And then we will multiply the answer by 2. So now I'm going to go back, and instead of doing it in degrees, I'm going to do it in radians. If I do that in radians, 3.14, right? So theta over 2, yeah, I'm just going to say it's approximately 2.3 radians. So then theta will be 4.6 radians. Okay, so if theta is 4.6 radians, so then we can go back. That point P, right? Okay. So if we want the distance that he swims, that chord is going to be 2r times the sine of theta over 2. Let me see. So that we get theta is about approximately 4.6 radians. Okay, so let's see if we can synthesize this information. So the chord length, let me copy this. Let's copy. So now we have the chord length is this. So that's going to be 2 times the 1 mile times the sine of 4.6 over 2. Again, this is in radians. So I'm just crunch that number. 2 times the sine of 4.6 over 2. And we are in radians. So I get about 1.49 miles. Approximately 1.49 miles. So then we need to find a P. Let me see. We need a little bit of context of like orientation. Choose it so that the chord length is about 1.49 0.49 miles. Or do it based on theta, which is like the 2 point. All right. So let theta, it seems like if we let theta be 4.6 radians. Okay, let's see how do we do. I'm just going to compare this to the text. Okay. All right, let's see how do we do. 4.6 radians. So now let's see here. As shown in the figure, the initial point is chosen arbitrarily and the terminal point at the other end of the diameter. The easiest way to describe the transition point is to refer to the central angle theta. If theta is 0, then the entire trip is done by walking. If theta is pi, the entire trip is done by swimming. So the interval of interest is from 0 to pi, which corresponds to the domain for inverse cosine. Objective function is the total time travel. So distance equals rate times time. Let me see if I keep going. So the time based on theta, I think this is what we have. Only solution, 2 times the inverse cosine of 2 over 3 is 1.6 radians, or about 96 degrees, which is the critical point. Okay, I think we made a mistake. 1.05 hours. Wait a minute, 4.9. 4.6. Cosine of theta over 2 equals 2/3, right? We have that cosine of, yeah, I got a negative 2/3. Subtract. Maybe that's where we're off. Should that be a minus? I got a negative 2/3. Subtract a third times 2 is a negative 2/3, but I got a positive 2/3. Oh, because cosine is even. So that means the inverse function is even. That's fine. Okay, so we can use the property that cosine is even and take this from a negative to a positive. That's fine. Let me see, does that change it? If we do inverse cosine of a positive 2/3 instead of a negative 2/3. Times 2, 1.68. So 1.68. Okay, that's fine. So I'm gonna say 1.68 radians. Let me see, I think that's what they got. Wait a minute. Theta minus pi. I did something in the setup incorrect. Because they get their minus in there and mine is not there. Pi minus theta. Okay, I'm gonna stick with using the fact that cosine is even. When we do the inverse cosine, we can change it to a positive. That's about the best I can do for right now on the fly like that. It might be a little off. You have to forgive me for that. I have to think about it a little bit more. Okay. .6 radians. Okay. 1 hour. So 1.2 hours. Okay, well. So that was a little bit fun. We didn't get that one all the way there. It really boiled down to the plus and the minus and some concepts from pre-cal, but that's just kind of how it goes. What's the time? We got about 20 minutes remaining. Let me look at this next one. Okay, so pre-cal is a little bit challenging. I'm gonna try this next one. And we're probably gonna make this the last one. I think there's one after this one. But let's just give this next one a go. All right. So we have this example 4, right? Let's go like this. So it says an 8-foot tall fence runs parallel to the side of a house 3 feet away. What is the length of the shortest ladder that clears the fence and reaches the house, assuming that the vertical wall of the house and the horizontal ground have infinite extent? Okay. All right. Okay, so we have the house. So we have this image going on. It says, what is the length of the shortest ladder that clears the fence and reaches the house? So we have the fence, we have the ladder, and we have the house. So let's start by getting an expression for the length of the ladder. Okay, if we look at the larger right triangle that's at play, it says the fence is 3 feet from the house. We don't know the distance of the base of the ladder from the fence. And we have some unknown height. Okay. So the ladder, a squared plus b squared equals c squared. So then it should be the case that what? X plus 3 squared plus b squared should equal the length of the ladder squared, right? So let's see, can we find another expression for the length of the ladder? We want to minimize that length. We got the outer. I was like, well, maybe we can use a second triangle, the x to 8. Let's see. We got the x to 8. Okay, I think we can use proportions here, right? So what should be the case? It should be the case that what? Something like x divided by 8 should be the same as x plus 3 divided by b. I think that let's go with it and see what happens, right? So I'm just going to go with it. So we can use proportions. It should be the case that x over 8, that ratio should be the same as x plus 3 over b. I think this will work. Okay. So for instance, if we were to solve for b is going to be equal to 8 times x plus 3 over x. Okay. And then we can take this and plug it back into the other, okay. Hello? Okay. So then we can get the length of the ladder would be x plus 3 squared plus this 8 times x plus 3 over x squared, right? And so now at this point, we would have an expression for the length of the ladder in terms of one variable. We want to minimize the length. Notice that I was kind of hoping it would be concave down. We have a parabola. Oh, okay. A parabola that opens up, right? Because it's one variable. Actually, we take the square root plus or minus. So I guess we would have cases, because if we have L squared, if we do plus or minus, we have the top part and the bottom part. If we want to minimize, we should probably take the bottom, which will be the negative. Okay. So this would be kind of like a circle, so we would be looking at the bottom half of the circle. Now, can we do that in this context? Okay. So let's see, we get L equals, now we have this plus or minus the square root. We got this x plus 3 squared plus 8 times x plus 3 over x squared. So then if we did cases, we could do the plus and the minus. Let me see, can we simplify this? Let's simplify this down some. So then we can have x squared plus 6x plus 9. 8x. 64x squared. 16x. 64 times 9 times 3 is 24 squared. Hey Google, what's 24 squared?
24 squared is 576.
That's gone. It turns into that. Okay, so what I'm gonna do, let's see, so let's get a common denominator of x squared. This is going to become what? X to the 4 plus 6x cubed plus 9x squared plus 6x squared plus 16x plus 576 all over x squared. We want the square root of all of that. If we combine like terms, we got this x to the 4 I think this persists. 15x squared, 16x, and 576. I don't know that I'm able to factor that. We're going to have the square root of this over absolute value of x, essentially. Because when you take the square root of something squared, it forces it to that positive. Let's see. Can we factor that? Now we could do synthetic division to find some zeros. Can we factor by grouping? Let's see. If we do synthetic division with a 1, that's a 1, 6. Let's see. I might look at the graph. I'm trying to think. Because we would need to be able to factor this. So we need to find the zeros. Let's see. So we have one critical value of 0 from the denominator. If we could factor that, we might be okay. Oh, and then that should be 6x cubed. If we let that be a 1, 1 comes down. 7, 22, 28. And that doesn't work. What's my time? Okay, let me think about it. I gotta think about this one. So this is where I would get stuck. Let me think about it. Okay, now if we did factor by grouping, will that help us? We could factor out an x squared. Let's see. Let's see, I'm going to use my calculator to see can I find some of those zeros quickly. So if I go to my y equals clear, I'm going to type in this x to the power of 4, 6x cubed, 15x squared, 6x, and 576. Okay, I'm just going to look at the graph. No zeros, no simple zeros. Let me look at the table for this. This is a degree 4. That seems to be getting worse, so there might not be any zeros. So maybe just 0, just the origin. That doesn't make any sense though. Oh, what am I missing? Maybe my proportion isn't right. Oof. Can't do them on the fly like I used to. Oh. Okay. I had to think about this one. Let me see. Okay, so the text, they said, first we ask why we expect the minimum ladder length. Let me see what they say. We could put the foot of the ladder far from the fence so that it clears the fence. So there is a range. Yeah, right? We got this L squared equals x plus 3 squared plus b squared. We got that. Yeah, so I think we just need to keep going with the factoring, which I'm just avoiding. 3. Did we make a mistake? It looks like negative 3 should have been 1 over x cubed. Oh, and that's supposed to be 64. Okay, well, there's one mistake. Yeah. Okay, so 8 times 8 is 64. Okay, let me back up to there. So let's see if that makes a difference. So this right here, that's supposed to be 64. Okay. Maybe that'll make the difference that we need for factoring. Yeah, if you make like one mistake like that, it does throw the factoring off. Let's see. So then we'll get plus or minus. Now I got a common denominator of x squared. So then we got x to the 4. Nope. We got x to the 4, 6x cubed, 9x squared, 64x squared, 16x, 576, all over x squared, and we're taking the square root of all of that, right? Okay. So then we get this, 64, 74, 73. Okay, so then with that, and this stays like that, like that, like that. Okay, so then let's go to our y equals, and that's supposed to be x to the 4. Man, I'm still making mistakes. X to the 4, 66x cubed, and it's supposed to be 73x squared. And then I think that's supposed to be a 16x, which I didn't have typed either. So if I insert a 1, okay, let's give this a go. Still not getting my 0. Yeah, I'm gonna have to think about this one. What's the time? So I'm gonna give myself another 10 minutes, and then I might just like put it down and come back to it. Let's look and see what they have though. So we got that. We got that. They left that. They got the 64. Let me see. Common denominator is x squared. So that plus that equals this. Maybe we should not expand it. Okay. Let me see. Maybe that's where it was throwing us off, is because we're expanding it and it's making it worse. So instead of expanding it, let's back up again. Let's get rid of all of this. So then L squared, let's see. So we have this x plus 3 squared. If we distribute 8 over x, that's going to be an 8 plus 24 over x squared. We still had to expand it though. Is there supposed to be a minus in there? Oh, okay, I see it. Oh, man. All right, so right here, we have this, right? L squared equals x plus 3 squared, and then we have we can look at this as, or from here, they both have this x plus 3 squared that we can factor out, right? We has a common binomial factor. So then L squared is going to be x plus 3 squared, and then we're going to be left with 1 plus 64 over x squared. I think that's it. That's what I've been trying to get to this whole time. Okay, that's the factor form. That looks much better. Let's see. 1 plus 64 over x squared. Okay. Let's see. All right. So yeah, this actually helps out a lot. So now that we have it in factored form, let's see if we distribute, will that help us? No, because it's going to take us back there. I want to look at one other thing and then we'll come back to it. So we got that. At this juncture, we could find the critical points of L by first solving the preceding equation for L, then L prime. However, the solution is simplified considerably if we note that L is a non-negative function. So the length, therefore L and L squared have the local extrema in the same point. So we choose to minimize L squared. So the derivative of L squared, d by dx, okay. So the function is going to be non-negative, so we can just take the derivative of this function as is. So we can take d by dx of L squared, because again the function is non-negative, so it's going to have the same critical value. So then if we take the derivative of this thing on the right, d by dx of this, 1 plus 64 over x squared, okay. So then we have to use what, the product rule? So the first times the derivative of the second So that's, let's see, that 1 goes to 0. 64 times x to the minus 2, 128, negative 128 x to the minus 3. So that's the first times the derivative of the second plus the second times the derivative of the first. Daggone it. That's going to be a 2 times x plus 3. I think that's it there. Let me kind of get this on one line. Okay. Okay. Now can we set that to 0 and solve for x? Let me see. We need to try to simplify that. 2, let me see, they both have at least an x plus 3. Okay. So let's factor out the x plus 3. We're going to be left with we can factor that out. So we're going to be left with, we got an x plus 3 remaining, but we still have this negative 128 x to the minus 3. And then over here, we're going to have 2 times 128 over x squared. Okay, nothing to distribute there, and we could distribute there. So let's go ahead and distribute. See if that helps. If we distribute, that becomes a negative 128x squared, which is what we want. And then 3 times that is going to be 300, 3 times 360 plus 24, 384. X to the minus 3. Okay. And then I think we still have this 2 and this 128 times x to the minus 2. And here this is minus 2. So then this cancels, which helps out a lot. Okay, and it looks like it becomes x plus 3, negative 384, x to the minus 3 plus 2. Okay. So then we could set that to 0 and solve. Negative 3, let me see. Did we take the derivative? Yeah. Okay, let me distribute and see if I can get to where they are. So if we FOIL first and first, think about it. First times first. I feel like this is going to get worse and worse. So this times that and that times that. This times that is going to give us a negative 384 over x squared. Outer is going to give us 2x. Inner, see that number is getting even worse. Hey Google, what's 384 times 3?
The answer is 1,152.
So then 384x, 2x to the 4. No, I feel like this is going away from where we want. Give me a moment. We're like right there and it's like irking me. 2x plus 3. We got that. All right. Multiplied everything by, let's see there, factor and simplify. Seems like we should get some things to cancel. We got one thing to cancel. But that 384 looks bad, right? Let me back up to here. What's the time? Okay, I'm gonna wrap this one up. Let me think about it. Give me a moment. I feel like we're right there. We got our x plus 3. The 2's are 2 there. We could factor out a 2. Or is it going to be a plus 1? There is a plus 1. Let's factor out. Is it a negative 2? Okay, let's factor out 2. Let's see. If we factor out that 2, x plus 3, so that would be what, 219, 192? Is that a perfect cube? Hey Google, what's the cube root of 192?
Cube root 192 is approximately 5.769.
X cubed minus 192. Okay, so we finally got there. We got this. We got our x cubed minus 192 over x cubed. This is fine. That's what they have. Oh boy, oh boy. Let's see. So we got to work on our factoring. And then we would have to say 2x cubed, right? Oh no, we're multiplying, right? So this is going to be 2 times x plus 3 x cubed minus 192 all over this. Okay, that's just multiplying fractions. Man, that was an adventure. Okay, so if we get this, the critical numbers will come from setting the numerator to 0 and the denominator to 0. So that was definitely some work to factor that, right? So you can see the notes. I know it was like a lot of back and forth, but we eventually got there. Okay. That was bad. Let me see. So then we get this x cubed minus 192 equals 0. Cube root 5.77. Okay. All right. So from there, we could set it to 0 and solve. We can't have a negative ladder length, so the -3 wouldn't work. So then, and x equals 0 doesn't make sense either in the context. So then the prime candidate would be here where we have this x cubed minus 192 equal to 0. If we solve, add x cubed equals 192. So then x is approximately, yeah, sorry about that, guys. Look, you just have to do the best you can. Just do the best you can. If you're ever having any trouble with anything, just reach out and we can talk about it, okay? And like kind of hash it out a bit. Let's see, 192 to the power of the cube root, so a third. Okay, yeah, we get it. So 5.77. So then this would be a candidate. This would be a critical point. You can continue with the first derivative test. Choose a point to the left and right to show that there's a sign change in the first derivative. And that's how it goes. So the trouble there was factoring. At least that's what kind of got me, was all the factoring of that. So, you know, it just kind of goes like that sometimes. But you can see all the work here based on that image. You know, it was a bit of a stretch. So we used Pythagorean theorem initially, but then we were trying to get that initial function in terms of one variable alone. So then we used proportions. So then it should be the case that x divided by 8 should be the same as x plus 3 divided by b. I think that's how that goes, right? So then we got b in terms of x alone. So then we were able to get the length of the ladder in terms of x alone. And then, because when we have L squared, because L is non-negative, we're not going to use the negative square root, right? That's a non-negative length. So the critical numbers from L squared should be the same as the critical numbers from L. All right. So then we take the derivative. We didn't have to introduce the square root, because that's what I initially tried to do, was introduce the square root, but we don't have to. We take the derivative here, we use the product rule, and then through some considerable like simplification and factoring, we eventually get to this point here. So then at this point, the critical numbers are going to come from where the numerator is 0, the denominator is 0. If we set the denominator to 0 and solve, we would get that x equals 0. But a ladder length of length 0 doesn't make sense in the context. So we wouldn't use that. If we set that first factor, x plus 3 to 0, we would get x equals negative 3. Again, a negative 3 doesn't make sense in the context. So the only real candidate will come from the x cubed minus 192 equals 0. And then from there, we get that x is approximately 5.77 feet. Okay. So, yeah, you have to forgive me for that one. You know, it was bad. We just have to do the best that we can and just kind of work it out. Again, as you kind of work through these examples, just do your best. If you're having trouble, link up with a tutor. Contact me and we can talk about it. We can hash it out, and I'm open to ideas. But you guys seem like you're going strong. As I kind of look at grades and kind of check on you all's status, you all seem like you're fine. So I'm just here for support. But that's how it goes. Okay, just know that you know I'm here. You just have to do the best that you can. Okay, let's see. So again, to recap, we have, and I might redo that one. I need to redo that one, but I'm like totally tired now. So on Moodle, we need to make sure that basically we have an assessment that's there that needs to be submitted. We have a participation and honesty quiz that needs to be submitted. So there are 2 quizzes on Moodle. We need to make sure that those are submitted. Otherwise, let's get our assignment submitted on Pearson. Okay, just as promptly as possible. You get unlimited attempts, okay? And you have support. You can ask me any questions. Make use of the Ask My Instructor. Link up with the tutor, okay? You have to do the best you can. All right. On that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace.